Hello, my name is Robert Mitchell, and today Electropages is here in Embedded World 2024 in Nuremberg, and we are at the Samtec booth, and we've got my best friend, Matt Burns.
Good to be with you again, Robert.
How are you?
Not too bad.
Not really my best friend, but kind of.
We're good friends.
I don't know.
He doesn't want to admit it, but we're good friends.
Good friends, we're good friends. Right. Anyway, so what's going on here today?
So, Robin, it's so good to have you guys here. We love working with Electropages. You're great. You guys are one of our great partners. So, thank you so much for that. Here at Embedded World, one of the things we want to focus in on are some of the high-performance interconnect solutions that we have that are proliferating across embedded solutions.
Yep.
So if you look at the board that's right here next to your left hand, this is a SI evaluation platform for our Accelerate HP interconnect series. That's the same connector set that's used for COM HPC, server, client, and mini modules. It can support 112 gigabit per second PAM4 performance, which we're showing on the Rohde & Schwarz VNA, up to 43 gigahertz. We can talk about the SI metrics in a second. But from a protocol standpoint, this connector can support PCI Express 6.0. It can support 100 gigabit Ethernet, InfiniBand, all sorts of. I know you're making. I know it's high speed, right? It's crazy. It's mind blowing.
It's too fast.
I'm sorry, but it's when you walk around the floor here at Embedded World, that's what people want to hear about. And like, look, we got the connector set to solve your solution. One other feature about the connector, it's high performance, it's high density, it's also open pin field array. So what that means is that any one pin can be a differential pair, a referential, a single-ended signal, or carry a high amount of power.
Differential.
Yeah.
Oh, fantastic.
So yeah, so the high speed are differential signals.
I think what I find absolutely fascinating about this. So right now, did you say this is 112 gigabits?
It is.
And the length of the cable for 112 gigabits per second, I find is absolutely phenomenal.
Well, bear in mind, let me just make one step clear. This is a test setup using the VNA. So the data here is actually de-embedded from the system. So when you're looking at the test results on screen, we've got really good insertion loss at 28 gigahertz. We've got really good return loss. We've got really good TDR. You can see the open eye diagram. We're actually testing this from this RF connection point to this RF connection point. So the cable length may be a bit of a misnomer for someone that's looking at this for the first time, but when you're testing a high-speed embedded, connector set, you actually de-embed the system. What you want to look at is the performance of the connector. You don't want to look at the performance of the cable plus the PCB plus the connector.
Oh, you're talking about the connector itself.
Exactly.
Still though, I still find this setup really impressive. And I'm looking at the eye diagram, and I can see three clear areas of empty space. So I'm assuming that there are three. Are there three voltage areas?
That's a good eye. It's very good observation on your part. It's PAM4 encoding versus NRZ encoding.
And how exactly does that work in terms of like the voltage levels and stuff?
So in short, when you use NRZ encoding, you send 1 bit of data per clock cycle.
Yep.
But with PAM4, you're actually sending 2 bits of data per clock cycle.
Is it double data rate?
It doubles the data rate, but at the same frequency. So you can get more, when you look at the frequency spectrum, you can get more data through the Nyquist frequency. The trade-off is the SNR of the signal it's more of a challenge, so you have to design the receivers to be able to handle that susceptibility. So PAM4, 4 voltage levels, we've got 3 open eyes. This looks really clean. That connector works for PAM4 encoding.
And so it is 4. So it's 4 different voltage levels to represent 2 bits.
Exactly.
And so that way you can work at a fourth of the frequency. Does that make sense?
That's exactly right. So
112
at 112, your Nyquist is at 28.
That makes sense.
Yeah.
Because one thing, because I remember having a conversation some time ago in another meeting where I was confused, thinking, is that 112 gigahertz of signal? It's like, no, it's reduced.
It would actually be 28 gigahertz.
That's right. It'd be 28 gigahertz. Is 140. That's right. And so that's how you're able to push that extra amount of data. But the only reason why you can do that is because your connectors have that signal to noise ratio, kind of like quality. So with a high signal integrity, so you can have those clear separate voltages that aren't kind of fuzzy to each other. That's absolutely fantastic. So, right. So in terms of like the absolute highest frequency, because obviously if 28 gigahertz is like your 112.
Yeah.
How high do you think you can currently push this kind of technology?
Well, in this interconnect, we're probably pushing the max at 112. But where the data center industry is going, a lot of this is coming as a result of AI disruption. We're looking at next generation speeds at 224. So 224 PAM4.
224?
Exactly. Gigabits per second.
It just doubled.
It just doubled. So from a Nyquist standpoint, you're looking at 56 gigahertz.
Oh my word. It just, I thought it was going to be like incremental, like, here's an extra few gigahertz. No. Blimey.
Yeah, if you look, I don't know if you paid attention to what happened at GTC a couple of weeks ago, but Jensen from NVIDIA is and launching next generation AI chipsets, and he's basically saying, you guys aren't going fast enough. We need more data.
Oh my.
So the whole industry, whether
God.
that's the chipset vendors, the interconnect vendors, the EDIP guys, or even the PCB vendors with their technology, all focus on getting to 224 as fast as possible.
And so to be absolutely clear, this kind of technology, you're using it in server systems where you're trying to interconnect different racks across backplanes.
Yes.
And if I remember correctly, actually it was right there actually on the screen, the flyovers. Yeah. So if you've got like an actual server itself and you want to get data from the front to the back, that's where your flyover technology comes in. And am I right in thinking that's also 112?
The cables are 224.
224?
We can get to 224 in the cables. We're actually working on the connectors on either end to get to 224.
So it sounds
the cable itself works great. It's the actual termination, the interconnect.
So you're struggling with the termination because the cable's too good.
Basically, it's a terrible problem.
Blimey.
It's a terrible problem to have. But we're real close. We're real close. We've actually over the last 6 months, we've actually demonstrated our next generation interconnect, SciFly HD. We're looking at some flyover OSFP solutions. Not really displaying that here at Embedded World because it's not really a solution that makes sense for this customer base. But when you look at some of the high-speed shows that we've gone to, that's where we're going.
So why is it that connectors are a lot harder to sort out than the cable itself?
The cable, that's a good question. So the cable itself, think of the cable as the PCB.
Yeah.
Right? PCB, you've got a signal trace on the PCB, vias, et cetera, et cetera. The cables in general have 1/3 the loss of the PCB.
Yeah.
So getting the signal through the cable is easy. But when you transition to the interconnect, that's where you can have some impedance mismatches.
Material boundaries and stuff.
Exactly.
Right.
So our general thought process there is design the contact that you can attach the solder or the cable directly to it, and then take the signal from the cable to the contact directly to the PCB. But designing the contact, not only is it the high speed, but it's also high density.
Yeah.
So we have a interconnect solution that routes 64 differential pairs in a 14 millimeter squared area at 224 each. So it's about it's like 12.8 terabit per second in a 14.
Sorry, did you just say 64 differential pairs?
In a 14 millimeter square area. So it's about 13 terabit per second.
That's like 7 millimeters by 2 millimeters.
14. It's 14 millimeter by 14 millimeter.
Oh, 14 millimeter.
Yeah,
14
millimeter
That's
square.
not 14 millimeter square.
14 by 14. Sorry.
No,
You're right, area-wise, but 14 by 14.
But still 14 by that's it. That's
small.
insane.
Yeah.
64 differential pairs.
But that's where the data center's going. Not so much here in embedded.
It's too much data. It's too much data.
It's not enough. I hate to say it,
not
but it's
enough data. Oh my word.
I didn't mean to stump you, by the way. I really stumped you. You're not a stumpable guy, by the way.
It's just too much data.
It is too much data.
And so what you're saying is that, and this is why this kind of technology is so important because things like AI and the development around it's going too fast.
Exactly.
And I think it's also right to say that would it be right to say that PCB technology can't keep up?
It's evolving quickly.
But not quickly enough because
not quickly enough because again. The general rule of thumb that we see when you look at our cables is about 1/3 loss versus what PCBs. Or you're getting something with a really low decay that costs 5 to 10x what a standard PCB would cost.
Yeah.
So it's a trade-off of a more expensive PCB or changing the architecture.
I get that, yeah. Because I think I know as well that if you want to get a signal across a very large PCB from the front to the back, you have to use a
retimer.
Retimers, retimers and boosters and stuff. Try and keep that signal integrity high.
Yeah.
Which is expensive and complicated. But like with your flyover, it's just whoop, from the front to the back, and it's right there.
Yep.
So one thing I wanted to ask you as well is what Samtec is doing in terms of things like fiber optics.
Good question. We see a lot of demand for fiber optics and embedded. For embedded applications.
Really?
Most interconnect providers, or most system designers, when they think of fiber optics, they think of something that's on the front panel because you have an active optical cable, or you've got fiber optics coming out the front channel. We see a lot of value add in putting the fiber optic transceiver, the optical engine, directly next to your chipset. So it's a mid-board optics or an on-board optics application.
Oh yeah.
So the signal integrity going from the chip to the optical engine is very short. Then you get the optical domain as quickly as possible, and it works great. Midboard optics is not generally adopted in data center applications, but it's ideal for embedded. So our midboard optical engine, which we call Firefly, finds
Yes, I remember this.
finds a ton of homes in embedded applications. So currently Firefly gets 28 gigabit. We're working on 32 gigabit, which supports PCIe 5. Then we're looking at next generation, different platforms.
And I remember this because I always found it quite strange how the fiber optic technology was actually was harder to achieve than the copper cables.
Yeah.
Because, and if I remember correctly, it's not the fiber optic itself. It's the connectors. It's trying to take those light pulses and trying to turn it into something that can be converted to an electrical pulse, and then getting that into your chip.
Or vice versa.
Or vice versa.
Right? Because it's when you got your transmit obviously going E to O, and then when you're going receive, you're going O to E. It's not that the optics can't support the speed. Is can I create an optical engine that's small enough while also having the PCB level attached, whether it's interconnect or whatever, that can support those data rates as possible. Firefly does that for 28. Works great for embedded. We're coming up. We've introduced a new platform we call Halo, which provides us a road mount to 56 gigabit, 112 gigabit optics, 64 as well, support PCIe 6. So yeah, there's a lot of work that we're doing in optics as well. We could probably spend a whole hour webinar or something on that talking about the technology, but we're working on that as well.
And I suppose if I'm right in thinking this, if you've got a limitation in trying to turn electrical pulses into light pulses, which itself is a very difficult process, I take it that you might be working on like multiple spectrums to try and increase the the bandwidth by having multiple channels.
There's several ways to attack that problem, but we try to do this simply as possible. One signal per fiber. Yeah. So it's a single mode fiber is just easier for us to work with. If you're looking at multi-mode, you're looking longer distances. We're trying to go 100 meters, we're trying to go 100 miles.
And I suppose multi-mode also has the issue that, again, the size of your receiver is going to significantly increase, which makes it harder to interface with your circuits.
It depends upon the optic solutions and the electronics that you have inside the optical transceivers. We try to keep ours as simple as possible.
That kind of makes sense actually. So you can refine that, make it so. Because I know one issue that you tend to have with things like optical components, that it's quite hard to try and switch them fast enough to squeeze the data out. So is that where things like gallium nitride might become useful because it's high frequency?
That's a good question. I tend to think of GaN technology more for RF than for optics. The challenge that you're talking about there is how long do the lasers fire?
Essentially, yeah.
Yeah, the lasers are their lifetime is dependent upon two key factors: how many transitions and how much heat. So you try to get the heat out.
They degrade.
They degrade over time. Yeah.
Oh.
So there's a lifetime for optics, especially for embedded. But you can overcome it. There's design hooks, there's design approaches, there's design things you do. So
I didn't expect that.
For using optics in a rugged application where it's thermal, you can put heat epoxy on. You can put advanced thermal interface materials. You can put it in a water-cooled system, whatever. There's ways to overcome it, but it's definitely a design challenge. It's not insurmountable.
But it
does
sounds really
take extra
difficult.
work. If you know what you're doing, it's not. If you're getting into the market or you're looking at it for the first time, it's like, oh my god. But it's really not that bad.
Yeah.
If you know what you're doing, or you're working with a partner like Samtec that knows how to design around it.
And I suppose that, and this is something, and I'm curious about this because I've seen this with a lot of other businesses at the moment where they're kind of going towards solution services. So instead of just providing you with connectors, they're going to try and get involved. So is that something that Samtec is looking to do?
In general, yes, Robin, because one of our mantras at Samtec is sudden service. It's not only about do we have the technology available to get that to customers within their supply chain, but we also look at that from a technology standpoint. So we provide high-performance interconnect solutions. We're not just trying to sell you a widget. We're going to provide you with the design services or the customization to answer the technical challenge or the design challenge that the electrical engineer, the OEM, the system architect has to help overcome it. So it really is a interconnect solution, not just a connector. Of course, if someone wants to come and buy, 500,000 2.54 millimeter headers, we can do that all day long, which is great. Yeah, exactly. And we still do that because that's our legacy business from when we were founded almost 50 years ago. But the focus of most of our engineering is next generation high performance interconnect solutions.
And so that really puts you on the bleeding edge of technology.
It does, in a lot of different areas. And optics, copper, RF, the whole shebang.
And I think it's also important for the audience to know as well that because we were talking before this whole setup, where you were saying that obviously signal integrity is key to Samtec.
It is.
But you don't want it to be the only thing that is associated with Samtec.
No, because we've got We've got 80 signal engineers that work for more than 80 signal integrity engineers that work for Samtec around the globe.
Yeah.
That's great. That serves that niche.
Yeah.
We've also got a growing team of optical engineers that are targeted at helping optimize the optical engine. We've got RF interconnect engineers that are designing RF interconnect from DC all the way to 110 gigahertz.
Yeah.
So, and there's other technology we're working on, material science, plastics, blah, blah, blah. A lot of those are behind the scenes that the customers aren't going to see, but both customer facing and behind the scenes, our teams are focused on doing the R&D and the technology research to come up with solutions our customers and our partners need.
See, fantastic. Well, just before we wrap up this video, I've got one more question for you.
Sure, Robin.
One more question.
Yeah.
For it.
You promise? Last one?
Yes.
Okay.
For the viewers who are currently watching this video, if they wanted to get involved with Samtec Solutions, what would you recommend they do? Visit
our website. That's the easiest thing to do, samtec.com. Or if they have a relationship with one of our existing sales team, that's a great way to get in contact and work with us as well.
Fantastic. Thank you ever so much for having us today.
Robin, good to see you. Thank you.
Thank you.